the concept of a planar graph. And so you see right here the definition is that a graph is called planar if it can be drawn on the plane, a flat surface, or in two dimensions, without any edges crossing each other. So if you have a simple graph that you've used before, so let's say a 3-cycle here, that's already drawn with nothing crossing, so that would be planar. The more interesting problems are going to be ones where you draw it, and the way you first drew it, it does have crossings. For example, right here, these two have crossings. This is our K4 graph. And so you might think that that is non-planar, but you can actually redraw this, or in other words, you can draw an isomorphic graph where you have one diagonal in the middle and one diagonal that goes around the edge here. This is also K4. And as long as there's any one way to draw it that doesn't cross, then that means K4 is a planar graph. Now, if you had K5, and we were to draw this here, there are lots of crossing edges. And it turns out that you can prove that no matter how hard you try, no matter which way you try to draw on the paper, there is no way for this to be drawn without a crossing. So this is an example of a non-planar graph. So if I give you a random graph on the test and I ask you, is this planar or not, then you want to try to rearrange things and try to draw it so that it has no crossing edges. And if you can, it's planar. And if you can't, then it's non-planar. Now it turns out that anytime you have a planar graph, you have this something called the Euler's formula. So Euler is the guy that created graph theory. He also did a lot of other things in mathematics, but for this, what he did was he showed his formula is that you will always have r equals e minus v plus 2. Now let me explain what that is. I will go ahead and draw my K4 in the planar drawing of it. So we're going to have E is the number of edges. So in this case here, 1, 2, 3, 4, 5, 6 of them. V is the number of vertices, 4. And R is the number of regions that this separates things into. So it looks like I have 1, 2, 3, and then the outside region, that is another region, that's going to be 4. And so let's check whether that works here. Is it true that 4 equals 6 minus 4 plus 2? That does check, and we get the right answer. If we do something even simpler here, let's say we just have the triangle that we already said was planar. This is only going to have 2 regions, the inside and the outside. And then my formula would have E is 3, V is 3, R is 2, and then you can check 2 is equal to 3 minus 3 plus 2. So it's just a kind of nice little formula here. It can be useful in other problems where you're applying graph theory to them. I use something like this in complex analysis as well, but regardless, it's a really cool little theorem here. And the last thing that turns out that it actually answers everything we ever want to know about planar graphs is that it tells us a criterion for when we are sure it's going to be planar or non-planar. It is an if and only if theorem, so it goes both directions. And what it tells us is that we are non-planar if and only if we either have a subgraph that is K3,3 or we have a subgraph that is K5. So if you look at your whole complicated graph and you can't find a K3,3 part of it, or you can't find a K5 part of it, then that means it's going to have to be a planar graph somehow. Maybe you can't see how to redraw it, but if there's no K3,3 in there or K5 in there, it is guaranteed to be a planar graph. And so that is like the end of the story on planar graphs, basically.